Welcome back. This is the next video in our series about the Boyuurange A50, and today we've got it on the bench with some testing equipment, and we're going to go over the voltages, the operating points, show the power output, clipping points, and all kinds of fun measurements off the as-built model that we have here in front of us. Thanks again to the viewer who sent this to me to use as a test experiment. And I know we can get more out of this thing. I'll go over in a minute what the actual measurements were and show you on the scope, but I'm not surprised at all at what this amplifier actually produces compared to what it's advertised as. So let's jump right into the voltage measurements and the analog scope measurements. I mean, as you can plainly see, they have on here, please don't share at website, thanks. Well, considering this is a schematic that they did not come up with, this is a copy of a schematic that's been on the internet and republished for at least 30 years. I don't feel like I'm sharing anything that's not readily available, so we're going to ignore their little please don't share thing. This is a power supply. Here's the 5Z3PJ rectifier tube. It's got a 385/0385 power transformer. And before I go any further into this, even though this says 110 volt 4 amp, they're clearly putting a 120 volt power transformer in these amplifiers now. When I measured the filament voltage at the driver tubes, which is supposed to be 6.3 volts, I had it on a variac and slowly pulled up the line voltage until I saw 6.3 volts here, and then I saw 5 volts on the filaments of the 300B, and when I measured the input voltage, it was 120 volts. So this amplifier won't need a bucking transformer for it to operate at the correct internal voltages. So I measured 385/0385 AC of the high tension power. Coming out of this rectifier tube, we're down to 403. Then they have a dropping resistor, which pulls it down to 395. And all these voltages are measured with the tubes in place and everything drawing power. So we got a couple of 33 UF chokes in series with balancing resistors across them, which will also act as bleeder resistors. And so putting these caps in series just raises their voltage rating, and they still will act as a 33 UF cap. Putting them in parallel would double the capacitance, but putting them in series, it stays the same and just raises the voltage rating. So this 400 volts that these caps are rated at are real close to what the power is here. And so I'm sure that's why they did this. Instead of spending the money getting a higher voltage rated cap, they just put two of these cheaper ones in series, which works. Next, we got two 5 Henry chokes that are rated at 300 milliamps. And again, I think they did this out of trying to fit these chokes inside the underneath side of the amplifier, and so they use, instead of using a 10 Henry choke, they use two 5 Henrys in series. One thing that I want to play with simming is adding a cap between these two chokes and see if that smooths out some of the ripple. There's a place inside here to fairly easily add one. And again, I'm going to put this on a simulator and see what that looks like. Okay, after this, we've got this voltage divider, with a cap on the negative side of the voltage divider. They've got this lead running to one side of the filaments of the driver tubes to raise the DC offset. I'm not a big fan of not creating a virtual center tap when you use this kind of scheme to raise the DC offset or create a DC offset. And so that's a change that I'm going to make, is using two 100 ohm resistors to split this DC offset to both sides of the filament on the driver tube. So at this point we got 390 volts going to the hot side of the output transformer, which leaves us with right at 380 volts reference to ground on the plate and 61 volts on the cathode with this 1K resistor. What they've got is 320 volts across the tube, which is a lot lower than what this tube can easily handle. Even these PS Vane made in China tubes can handle 400 volts across the output tube easily. And I'm a big fan of running as much voltage across the tube as you feel you can safely get away with. I did the math as well, and they're only running this output tube at 50% of what it's capable of. So one of my goals is going to be to raise the B+. When we come over here to, there's a couple of 20K resistors in parallel, which would be 10K of resistance going to the driver section of the amp, and this is the RC decoupling for the driver circuit so that the driver plate doesn't see the variations in the B+ going to the output transformer. So we come over here and we got 300 volts before the plate resistor, which is about 100 volts shy of what I ended up with in my amplifier to get the swing that I needed to really drive the 300B tube. So again, I want to get this B+ higher, likely put a smaller resistor, dropping resistor here, go down to 2 to 4K to try to get this 300 volts up a lot higher. Then they use this same scheme that the J.C. Morrison had with a 100K resistor on the plate with a 1K here. Then they have 62 volts on this plate going over to the grid of the second stage. Got 68 volts on the cathode. And there's a 33K and a 33K on each side. With a, it says a 0.47 UF 450 volt, but what's actually in the amplifier is a 0.56 UF at 250 volts. Given we're seeing 230 volts right here, that's really close to what the maximum that this coupling capacitor that they've used here. Plus it looks like a pretty cheap capacitor to me. It's just a little square looking, doesn't look like a very high quality coupling cap to me. So that's something else we're going to be changing. And the other problem I see with this design is they've got a 330K grid leak resistor, and I'm sure they did this trying to boost the power output. These made in China 300B amps really need something more like a 270K at the most for this grid leak, because the problem becomes if this resistor is too high a value and too much current comes off of the cathode leaking into the grid, that can cause a runaway red plate, and not something that we want to see happen in an amplifier. So I'm going to be dropping this down to a 270K. I'm going to drop this down to about a 3.3 or 0.33 UF coupling cap at a minimum of probably 400 volts. We'll see once we get these voltages all set. With my cascode, if I think this was a lower voltage, but I'd have to go back and look again. So my plan is to, on the driver stage, is to connect this plate to this cathode, get rid of this cathode resistor and cap, put an LED here to set the bias of this first stage of the cascode, and then pull this off the plate with a 27K dropping resistor here. But we'll get into that when we're redrawing the schematic. One thing I'm probably going to try before I mess with the driver circuit, for folks that feel that this may be outside of their skill, is dropping a 5AR4 rectifier tube in here and bypassing this dropping resistor, and see what bringing up the B plus on both the output tube and the driver tube does to the sound of the amplifier. The only problem I could see with just dropping this tube in and raising the B plus up is this issue right here, where we got 230 volts and this coupling capacitor is only rated at 250. If we bump this voltage up, then get this up to 250 volts, then we're risking blowing up that coupling capacitor. So to jack up the B plus, to try to get some more power out of this thing at lower distortion levels, we may end up having to replace this coupling cap anyway, which isn't a bad idea. So we're going to run through some of these different scenarios and kind of do levels of modifications on this amplifier so that people that have different levels of comfort going inside and changing a bunch of parts in the side of this amplifier can slowly change and improve this amplifier over time and as their skill set improves. So we're going to jump now to the next step in our testing process today. Now that we've checked all the operating point voltages and determined that 120 volt AC in actually brings us the correct heater voltages, etc., we're going to hook it up to my analog Tektronix scope with my TEMA audio generator and see where the clipping point is on this amplifier and take a look at the square wave. I'm suspecting that this is going to behave very similarly to the Sun Audio J.C. Morrison design schematic this is based off of, but they did change a couple of resistors on the driver's side from 27K to 33K, which might give us a touch of headroom before it starts clipping, but I still don't think we're going to be anywhere near what this amp's capable of. So we're going to start off with 1 volt peak to peak, and as you can see, we're on a half a volt per division here. And let's turn the volume up and see where the clipping starts. So far, everything looks good, and that's at about a little over half volume. And if we position these on top of each other, you can see that the output follows the input pretty closely. I think, at this level of output, this amplifier is probably going to sound fairly decent, or pretty decent. I mean, I don't know what the frequency response will be, but not seeing a lot of distortion there. But as we turn it up, there's the clipping. And it's actually pretty even on the top and the bottom of the waveform, which is nice to see. So let's get where the clipping is just gone, and then pull it down. And this is on 5 volts per division on the output, and I'm seeing 5, 10, 15 volts peak to peak, which is a little over 3 watts output into an 8 ohm load, which is right around what I was seeing on the 300B amp that I built using the J.C. Morrison schematic, maybe a couple of tenths of a watt more, but seeing the exact same thing, that once we start really pushing the amp, it ends up going into distortion way short of what a 300B amp should be able to produce. I believe most of this is going to be seen on the driver circuit, and we're going to switch the leads here and see if it is in fact seen on the grid of the 300B tube. But before we get into the grid drive, I want to look at the square wave coming out of the output transformer. And at 1 kilohertz, 1 volt in, peak to peak, and the amp operating at about 60%, 70% power in that range, the square wave looks fairly nice. It's a little rolled off on the bottom end and got a little bit of ringing here. As we turn up the frequency, there's 2K. Starting to see more roll off, a little more ringing. And as we go up, it starts getting a little uglier. We get some ringing here, but getting a lot of distortion of the both sides of the square wave. I do want to go ahead and see what it looks like at lower frequencies. And just as I suspected, we're seeing a lot of distortion at lower frequencies as well. So let's jump to seeing what the grid voltage is so we can put this thing on the audio analyzer and see what the real distortion figures are. Okay, so now we have the probe hooked up to the grid of the output tube, and I'm seeing the same distortion patterns that I was seeing in my amp based off this circuit on the grid of the 300B. And as you can see here, the fat upper section and the narrowed bottom section, and as we turn up the voltage or the volume, it gets even more apparent. And when we start trying to lay these on top of each other, see how rounded this one is and how spiky this one is? That's going to be some pretty heavy duty distortion out of the driver circuit, which is just getting amplified by the 300B tube. And right there you can see it's going into some pretty heavy clipping on the top side. So if we get short of the clipping and come down here with the 10x probe, and this is set on 50 volts per division when it's set on a 10x probe, we're getting just over 100 volts peak to peak out of the driver circuit, which is way short of what a 300B wants to see on the grid. Now this driver circuit is good at having a high input sensitivity, so if you've got a really weak input signal, this circuit might work well. But I feel like for most uses where people are using a phono stage that's got a fairly strong output, like 1 volt RMS, or you're using a DAC or a CD player that has 1 volt RMS, you don't need this high in input sensitivity. Now that will make this amp look like that it's got plenty of power if you're running it into some highly efficient speakers and you've got a really decent line in you'll be running it at probably a third volume and be thinking, oh, this thing's got tons of power, it's got plenty of headroom. Well, once you turn it up past half volume, it's going to get into almost unlistenable levels of distortion. So, this is no surprise. This is really what I was expecting to see out of this. And I think we can get a whole lot more power out of this amp by doing some modifications to it. The next thing I want to do is hook it up to the audio analyzer suite with the Audio Discovery 2 and see what the frequency response curve is and see how much distortion this thing's putting out at what wattage levels. So let me get that hooked up. So while we're letting the amp warm up for the next test, I thought I would show you the inside of the amp. We can go over this in more detail later, but as you can see, it's a nice layout. They've got the transformers, got 2 chokes, the gold cathode resistors for the 300B tubes are elevated off the circuit board so they don't overheat the circuit boards. The power regulator board is in the center with the 300B tubes on each side. And then up here in the front, you can see the point-to-point wired 6SN7 clone tubes that it uses. That's where we're going to be doing most of our work. It's really nice these are wired point-to-point because given that's the part of the amp that I want to rewire, it'll be much easier to do given that it's point-to-point and not a circuit board. And then here's the Audio Discovery 2. It's connected with the one lead off the top, comes over, goes around, goes into a splitter, and goes to the 2 input jacks. And there are my dummy load resistors. And then we hook the 2 channel probes to the output of the amplifier, which clearly we need to be using a dummy load on. And then they come back around and go to the channel 1 and 2 on the Audio Discovery 2. And then it's hooked up to my old ThinkPad that has got the Audio Suite software loaded on it. So let's run this thing through its paces and see what we get. This is the total harmonic distortion versus the input signal. And as you can see, it's got pretty low distortion until we get up near the higher end of the range. And where the cursor is right now is at 2% distortion, and it's making 2 watts of output power. And where the cursor is right now, it's got just under 3% distortion, and it's at the 3 watt range, which is what I saw on my analog scope where the clipping started. Like most tube amps, this clipping is pretty soft and you don't see a straight vertical line like you might see on a solid state amp. But this is the point that the input driver is starting to clip and that the distortion is starting to go up. I only track it up to 5%, and at 5% distortion, it's showing 4.68 watts, which is some pretty heavy distortion. So this thing doesn't even begin to make the 7+ watts that it claims that it makes. The next thing I'm going to do is do the frequency response sweep and show you the results of that test. Okay, here's the frequency response curve, and as we can see, it's pretty flat. It starts to flatten out around 20 hertz, and it rolls off pretty steep once you get past about 10k hertz, which honestly, that doesn't concern me a whole lot. There's very little music that's going on past 10 hertz or 10 kilohertz, and it's not unusual to see a 300B amp roll off on the top end like this. It's probably got something to do with the quality of the output transformers. But again, having a couple of decibels, even up to like 3 decibels roll off on the top end past 10K really isn't something that I'm too concerned with. The channels are fairly well matched. You can see a little bit of difference between the left and the right channel with the blue and the red line, but it's not anything I'm overly concerned about. The last test I want to run is the frequency versus harmonic distortion, and let's see how it fares in that test. So this sweep was done at a 0.5 watt out at 8 ohms, and it does really well here. It's below 1% distortion across the whole frequency range. There's a little more distortion on the low end, which is to be expected, but at low listening levels, this amp does seem to be pretty clean with a small amount of total distortion. I'm going to do the next sweep at 3 watts and see how well it fares closer to what its output actually is. So this is a sweep at 3 watts, and it's still nice and flat. It starts out around 3% and dips down to about 2.5 in that range and stays there pretty across the board. That's showing me that if all you really need out of this amp is 3 watts, it probably sounds really nice. I am going to hook it up and do some listening tests, which I haven't done yet. I wanted to run these measurements on it before I actually listen to it to make sure that the amp was operating properly and it wasn't going to harm my speakers, but I feel safe now to hook it up to my Clips RP600Ms and give this thing a good listen later today. And I will cover the listening parts of this in my next video. And now you can see at 5 watts, we're getting into some pretty heavy distortion. It starts out a little over 5%, and it never gets below 4.2 or so, which is clearly going to be audible distortion. So hopefully we can get this amp after some tuning to put out 5 watts, but have this distortion level much lower than it is as it comes out of the box. So as you can see, there's still a lot of headroom left in this amplifier, and like I showed earlier, I think one of the first steps is to bump up the B plus using a 5AR4 and bypassing the voltage drop resistor, possibly adding another filter capacitor, and see what we get just from doing those simple mods. We might be able to get another 0.5 watt or maybe more out of it. We need to get there anyway. And obviously I want to try the Cascode driver mod that I did on my own 300B build, and I think that's going to be what takes this amp where we want to see it, where it puts out what a 300B is actually capable of. As built, they're running the tube weak and really not much more power than you would expect out of an EL34 amp, and a 300B should really be almost twice that output. So let's see if we can get this thing there. So if you like this series, please subscribe to my channel, like the video, and I look forward to seeing you on the next round of 300B fun. Have a nice day.